In today's world of speed, ever-increasing speed, engineers and designers, manufacturers and maintenance men are challenged to find better ways to keep parts together. More speed means more stress from vibration and impact, and more need than ever before for better fastening methods. In today's world of speed, vibration and impact old-time fastening methods are outdated. Manufacturers have therefore developed new types of locking fasteners to keep today's equipment running and to make it safer and more reliable. How the best of these locking fasteners hold up is demonstrated by this modified Junker machine. The Junker applies severe shock and vibration stress to the bolted assembly and can be used to test service-related performance characteristics of various mechanical fasteners. This newly designed unit is a significant upgrade from a unit that was used to show the reliability of thread lockers over 30 years ago. This new test unit simultaneously measures torque and tension and allows for independent control of both the vibration frequency and intensity during each test. This unit easily demonstrates that thread lockers, in addition to sealing threaded assemblies and protecting them from corrosion, also resist shock and vibration better than mechanical methods. The Junker's transverse vibration loosening test provides a simplified method for broad-scale testing and inspection of the transverse vibration or loosening properties of fasteners. The Junker generates relative motion perpendicular to the axis of the bolted assemblies. A comparison transverse vibration test is designed to expose two or more fastener sets to identical test parameters, allowing the technician to determine the effects of a single variable on a bolted assembly. According to Gerhard H. Junker, the developer of this test, it is well established that a dynamically loaded joint fails in most cases either by fatigue failure or by rotational loosening of the fastener. Even the fatigue failure is often initiated by partial loosening. Results of the transverse vibration loosening test are useful for the development of bolting strategies which can reduce or prevent the risk of vibrational loosening in service or mitigate the effects of vibration where it cannot be avoided. To demonstrate how different fastening devices hold up to vibration, a simple test can be run. First, the technician will test the properties of a plain nut and bolt assembly with no mechanical or chemical locking device. To begin, the laboratory uses a 3/8" phosphate bolt to nut and a hardened steel lubricity washer. The motor speed is set. The bolt is then slipped through the load cell and the nut is spun down to the surface of the lubricity washer. The technician uses a wrench which is hooked up to the computer to read out the torque electronically to tighten the nut to a predetermined clamp load. The nut and bolt are marked. By marking the nut and bolt, rotation of the assembly is more easily observed. The technician begins the test. Over a period of 20 seconds, the assembly loses approximately 60% of its clamp load. Now the technician will test the properties of several other mechanical fasteners. To begin, the laboratory will place a split-ring locking device on the threaded assembly. The technician uses a wrench to tighten the nut to the predetermined clamp load. The nut and bolt are marked. Over a period of 10 seconds, the assembly loses approximately 40% of its clamp load. After 60 seconds, the test is stopped. The technician measures the breakaway torque of the assembly. Now the technician will test a chemical fastener on the nut and bolt assembly. A few drops of the chemical fastener, in this case Loctite-272, are placed on the threads of the bolt. The assembly is allowed to cure for 24 hours prior to the test. The nut and bolt are marked. During the duration of the test, the assembly loses less than 5% of its clamp load. After 60 seconds, the test is stopped. Modern-day cars, trucks, conveyors, and other high-performance equipment will continue to pose problems of fastener reliability and safety as speeds and loads increase. Designers, production engineers, manufacturers, and maintenance employees can solve these problems by turning from traditional fasteners to newer and better methods. Chemical locking, as we have seen, resists shock and vibration better than mechanical methods, and in addition, seals against leakage, resists against corrosion, and is suitable for high-speed production, and is vitally important to keeping pace in today's changing fastener world.